Hello everyone, this is Dr. Lennon, and we're going to take a look at our last two tests for convergence of infinite series, the ratio and root tests. And we'll just be looking at the hypotheses and applying a couple of examples. If you want to look at the proof, all of these can actually be proven essentially by kind of like doing a reduction to geometric and then comparing with that. So that's the main idea of the proof if you want to read about it. And the ratio is the more important of these two, I would say, just because it comes up when we look at radius of convergence of power series. So it's going to pop up again when you look at that topic. So, okay, so let's go ahead and look at the ratio test here. So, the ratio test, again, we just have an infinite series, so let the sum of AK be an infinite series. And we're going to let R be a special limit. So R is going to be the limit as K goes to infinity of the absolute value of the ratio of two consecutive terms, A to the K plus 1 over A to the K. So basically what happens, so this R is reminiscent of that geometric series, so that's why I was saying to think of that. And the conclusions are quite similar. So if this limit turns out to be less than 1, the series converges absolutely. And therefore it converges in all conditionally as well. Let's remember the stronger notion of convergence. If R is greater than 1, the series diverges. And if R is equal to 1, the test is inconclusive and you have to try and use another test, maybe a limit comparison or an integral test or something like that. So a lot of times these tests will involve things like factorials are a good indication that you're going to use a ratio test. Usually they give a lot of cancellation, so that's one reason why. So let's example. Let's go ahead and use the ratio test to determine if the series converge. So the first one we'll look at, A, we have the infinite series from K equals 1 to infinity of 10 to the K over K factorial. And remember, we're looking at just a limit. So evaluating this whole series comes down to looking at that limit. So we want to look at the limit as K goes to infinity. So the one that's on top is the K plus 1. So we have 10 to the K plus 1 over K plus 1 factorial. And then we're dividing by A to the K, which essentially means multiplying by the reciprocal of the fraction raised to the at the kth indice. So this will be K factorial over 10 to the K. So we get a lot of cancellation here, right? Because if we want to rewrite this, we can actually rewrite to show the cancellation a little bit more clearly. Remember 10 to the K plus 1 is just 10 times 10 to the K, and K plus 1 factorial is actually K plus 1 times K factorial. So usually I wouldn't write this out, but I will just to show the cancellation for this one. And then on the bottom, we're going to have a K plus 1 times a K factorial times a 10 to the K. So basically the 10 to the K's go away, the K factorials go away, and we've just got the limit as K goes to infinity of 10 over K plus 1, which equals 0. So from the ratio test, the series converges. So by the ratio test, the series converges. All right, right. Let's go ahead and look at another one. Let's say we're looking at the infinite series from k equals 1 to infinity of -1 to the k times k to the k over k factorial. So quite a confusing looking series. Again, remember the ratio test, we're taking the limit of the absolute value, so we can pretty much ignore that -1 to the k. The absolute value of that's just always going to go away. So what are we doing here? We're again just looking at the limit as k goes to infinity. Remember the k plus 1 is on top. The absolute value is just removing this -1 to the k, so we get k plus 1 raised to the k plus 1 over k plus 1 factorial, and then we need to multiply by the reciprocal, so that's going to be k factorial over k raised to the k. So the obvious simplification we can make is we can cancel k factorial and just leave a k plus 1 on the bottom. So what we're actually looking at here is the limit as k goes to infinity of k plus 1 to the k plus 1 over k plus 1 times k raised to the k. So if we look at this, they aren't too far off. K plus 1 is certainly greater than k, so we know the denominator is greater than k to the k plus 1. We know this limit is bigger than, I don't know if that is going to help us or if it's really important here. Probably it's easier to rewrite it like this. Just pull the k plus 1 out on top. So let's write it that way. Let's say we're doing the limit as k goes to infinity, and we write it as, we have our k plus 1, then we have k more powers of k plus 1 over k plus 1 over k to the k. So now those will cross off, and so our limit, if we continue down here, is the limit as k goes to infinity of, they both have a power of k, so we can actually write this as k plus 1 over k to the k. So basically, we're getting something that's going to, it looks like it's in determinate form right now because it's 1 to the infinity, but if we remember, actually this is a limit that's familiar to us. We can rewrite the inside as k over k plus 1 over k. So actually that inside limit is really 1 plus 1 over k to the k, and if you remember, that is the definition of one of our most important numbers in math. That comes out to exactly Euler's number. So this limit approaches e, and we know e is about 2.718, so that tells us by number 2 in the ratio test that the series will diverge. So by the ratio test, the series diverges. So a little bit, again, a lot of times when you're evaluating these series, some of the stuff can bring back a lot of those old theorems and limits. So if you're struggling to think about that, you may want to go review the limit chapter. So let's go ahead and do one more ratio test, since this is the more prevalent of the two that pops up with power series. So let's go ahead and look at C. Let's say we're looking at the infinite series of, let's say, -1 to the k plus 1, e to the negative k, which remember is just 1 over e to the k, times k squared plus 4. Okay, again, we're doing, with the ratio test, the limit of the absolute value of these ratios. So, in fact, we can ignore that -1 because we're using the absolute value. So, on top, we're going to have k plus 1 quantity squared plus 4. And on bottom, since it's e to the negative k, that will be e to the k plus 1. And then we're multiplying by the reciprocal e to the k over k squared plus 4. So immediately we can recognize that we've got kind of two parts here. The e to the k over e to the k plus 1, that'll just be a 1 over e. So we have a 1 over e, and then we've also got this times k plus 1 squared. We can multiply that out if we want. That's k squared plus 2k plus 1 plus the 4 is plus 5 over k squared plus 4. Again, when you're looking at a polynomial, you understand that you really only have to consider the dominant terms. So that's k squared over k squared. So the polynomial part's going to have a limit of 1. So really, we're just going to have 1 times 1 over e. You could also use L'Hopital's rule twice if you wanted to verify this. So this limit just comes out to exactly 1 over e. We know that's 1 divided by 2.718 about. So that's less than 1. So we know the series converges. Absolutely. So by the ratio test. The series converges absolutely. So let's go ahead and now move on to the root test. So the root test is going to have some very similar conclusions, but what we're doing is we're looking, rather than at a ratio, we're looking at taking a root, an nth root or a kth root. When I learned this stuff, they were always using n. Now in this text, they're always using k. So let a to the k be an infinite series. And we're going to use the Greek letter rho here. Let rho equal the limit as k goes to infinity of the kth root of the absolute value of a to the k. Now we're not using r here just because this isn't a ratio. Rho is like the Greek letter r, but it's for root here. Probably why we're using the different. Okay, so the conclusions. 1, if rho is less than 1, the series converges absolutely. 2, if rho is greater than 1, the series diverges. And 3, if rho equals 1, again, we are inconclusive. I've seen some textbooks nowadays only teaching ratio test and not root test, but sometimes the root test is just more convenient. I mean, a lot of times both tests will work or something like that, but a lot of times when you have powers, the root test just seems to be a little bit more convenient. So we'll look at 2 examples. So use the root test. To determine if the series converge. So A, we'll look at the infinite sum from k equals 1 to infinity of 3 minus 4k squared over 7k squared plus 6 raised to the kth power. Again, as you can tell, there's that kth power, which is going to make the root test just pretty much a little bit simpler than the ratio test here, I would say. So we're looking at the limit as k goes to infinity of the nth root of the absolute value of this whole thing. So 3 minus 4k squared over 7k squared plus 6 to the k. So that the k is actually inside, but they're technically equivalent, right? Because yeah, so it doesn't really matter if we write it like that or not. So the limit just simplifies to the limit as k goes to infinity of 3 minus 4k squared over so let's write it like this. Absolute value 3 minus 4k squared over 7k squared plus 6. Okay. So we know the bottom is always going to be positive, but as k gets large, the top is going to be negative. So the absolute value here would be equivalent to just the reverse order of the top, meaning this is going to be the limit as k goes to infinity of 4k squared minus 3 over 7k squared plus 6, and that is just going to have a limit of 4 over 7. So that is less than 1, so by the root test, the series converges. So this is less than 1. All right, so let's do one more. Let's go ahead and look at excuse me, the infinite series of negative 2 to the k over k to the 10th. So here we're looking at the limit as k goes to infinity of the nth root of the absolute value of this negative 2 to the k over k to the 10th. This whole thing raised to the, I did the n. I meant to write k for the kth root. Again, like I said, they used to use n when I did this. So, okay, so the top is pretty clear. It's just going to simplify. The roots are going to cancel. We're going to get the limit as k goes to infinity. So the top is, the absolute value is going to make that a positive 2. And then we're going to be dividing by the kth root of k to the 10th. Okay, so here is a useful thing if we haven't done this limit before, but for the root test it comes up all the time. So this actually just goes to 2 over 1, which is 2. And that's because anytime you look at the limit as k goes to infinity of k to the 1 over k, that is equal to 1. So essentially, we could break that up into 10 different limits of k to the 1 over k using the product rule for limits, and then multiplying them together. But since each one of them is 1 multiplied together 10 times is 1. So we get something bigger than 1, so that tells us that by the root test this series diverges. So that is the conclusion there. Again, you'll probably use the ratio test more in the future, but the root test, a lot of times, if you see a power in some series that you know you can get rid of, a lot of times the root test is a little bit easier to check and will get you to the conclusion a little bit faster. So anyway, that's it for the ratio and root test. This is Dr. London signing off.